Hi everyone, welcome to my channel. So I have got a lot of requests to do a series of lectures on elementary particle physics. So here it is. This is the first video of that series, and I thought why not start the entire discussion with a video on the fundamental forces of physics. So everything that you see in the entire universe, all the forces, all the phenomena, all the interactions that you see from the microscopic subatomic level to intergalactic distances can all be traced to or broken down into four fundamental classifications: the gravitational force, the electromagnetic force, the strong force, and the weak force. So in this video, I'm going to talk about these four forces in a very brief and concise manner. And this video is going to act as a springboard for further discussion of elementary particles. So let's get straight into it. So the first force is the gravitational force. The gravitational force is responsible for the large-scale structure of the universe and vast majority of macroscopic phenomena. For example, the reason I am standing right now on the surface of this planet called Earth, it is because of gravity. Without gravity, I would not be able to stand on this surface because the Earth is spinning on its own axis, and without gravity, I would be flying across in space. Alright, without gravity, the Earth itself would not be a round planet. All the mass came together as a collection to create an object known as planet because of gravity. In fact, it is gravity which gives the structure of the solar system. All the planets revolve around the sun because of gravitational attraction. In fact, all the solar systems revolve in the form of a galaxy with respect to some kind of a core because of gravitational force. The same force which is responsible for an apple falling down. If I throw something, it falls down. If I throw a ball or a projectile or a bullet, I shoot it somewhere, it falls down. That same force is responsible for the structure of the galaxies and the structure of the solar system. It is also responsible for tides. You see, because of the apparent motion of the moon around the Earth and the Earth's rotation, the water bodies, the height of these water bodies keep on changing regularly. These are known as tides, and this is because of the moon's gravitational attraction. Now, the same gravitational attraction also leads to the existence of our sun. You see, sun was originally a collection of gases spread out in space. They came together because of gravitational attraction, and now these gases, they have been concentrated in a certain region in space, and there is so much gravitational pressure, then that pressure leads to huge amount of temperature that leads to nuclear reactions. Now, nuclear reactions happen because of different reasons, but the pressure which is necessary to induce nuclear reactions is coming from gravitational pressure. So some of the properties of gravitational force is that, first of all, it is always attractive. It always attracts, it never repels. The gravitational force has an infinite range. It can act at short distances, it can act at very high, very large intergalactic distances. However, gravitational force is usually not responsible for interactions at subatomic level, because in subatomic dimensions, when we are discussing the interactions of protons and electrons and neutrons, the mass is so small and other forces are dominant that gravity is almost negligible. So gravity is not responsible for any kind of atomic or subatomic phenomena, but most macroscopic and large-scale behavior is a result of the gravitational force. The gravitational force acts on anything that has mass or energy, and it cannot be transformed or shielded against by any kind of a mechanism. Now, the very first scientific explanation for this kind of a gravitational force was done by Sir Isaac Newton when he gave his very famous universal law of gravitation, in which he said that two bodies which have different masses, they are attracted to one another by a gravitational force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Alright, so this is the force of gravity, which is proportional to the product of their masses and inversely proportional to the square of the distances between them. And using this very simple model, You can not only explain why an apple falls to the ground, you can not only explain projectile motion, but you can also explain the behavior of moon around the earth, the behavior of asteroids and comets and satellites, the behavior of the planets around the solar system. You can predict when a comet is going to come or revisit the solar system after a certain number of years. So this very simple model of the gravitational force given by Sir Isaac Newton was successful in explaining vast majority of the phenomena, like explanation of the orbits of the planets in our solar system, explanation of objects that fall in the gravitational field of Earth, etc., etc. However, there were few phenomena which this simple model was not successful in explaining. One of them was the Mercury orbit. You see, usually in Newton's law of gravitation, the kind of orbit that we see in the solar system for our planets is an elliptical orbit or a circular orbit. But in the case of the Mercury, the elliptical orbit was not exactly an ellipse, but rather it looked like an ellipse was rotating with time with respect to one of its focus. Alright, and that was something which was kind of confusing and not being explained by the Isaac Newton's law of gravitation. 100 years ago, a new theory of gravitation was given by Albert Einstein in his theory of general relativity, in which he explained gravity in a slightly different manner, but which was very much successful in explaining the perturbations in the orbit of Mercury, as well as in predicting certain very strange behavior with respect to the gravitational force. Now, how Einstein defines gravity is not as a force that is acting between two masses, but rather as a consequence of the curvature of space-time. Now you see, everything, all points, all objects in our universe exist in a space-time continuum. And this space-time continuum, according to Einstein, very much depends on the mass present at a particular point. So mass have the capacity of affecting the space-time continuum in a particular region, which leads to gravitational effects. So basically, objects want to move in straight lines. They want to go from point A to point B in the shortest path, which is nothing but a straight line, and which is also known as geodesic. Just to give you a small idea about what GDR is. But in the presence of a mass, when space-time continuum gets curved or distorted, these lines that represent the shortest path between any two points is not always a straight line, but rather they become curved. Alright, it can be shown by a very simple example of a heavy mass onto some kind of a trampoline or some kind of a plain elastic surface. It's not an exact representation, but it gives you an idea. If there is an object moving on this plane, it will try to move on a straight line. But if this particular plane gets curved, then the object's motion would also get affected. That is what gravity, according to Einstein, is. Einstein says that gravity is nothing but the consequence of the curvature of space-time continuum that is created by the presence of some kind of a nearby heavy mass. Now, this explanation is the modern explanation of gravity, and not only it explained what Newton's law of gravitation was unsuccessful in explaining, but it also predicted many other very interesting phenomena, such as gravitational lensing. So in gravitational lensing, distant objects, the light coming from distant objects gets bent around heavy star-like systems. It also talked about phenomena like gravitational redshift. So when light is emitted by a star, and as the light is trying to move away from the gravitational potential, its frequency changes. It also explained gravitational time dilation. That means if two people are at different locations with respect to a gravitational field, then their measurements will have a time dilation associated with it. It also predicted black holes, that there can be objects which are so massive and the gravitational force is so huge that not even light can escape those kind of objects, and they are nothing but black, so they are black holes. Anyways, that is all for gravitation. Let's move on to the next force. Now, the next force is the electromagnetic force. Can you think of what kind of stuff is happening in the world because of this particular force?
Well, a lot of things actually.
See, even though the electromagnetic force is responsible for electric and magnetic fields, but they end up creating a huge diversity of phenomena and objects around us. So for example, the atom. You see, what is an atom? The atom is a collection of positively charged nucleus and a bunch of electrons. Now they exist in the structure because of electromagnetic attraction, because the nucleus is positively charged and the electron is negatively charged. Whenever charges are involved, electromagnetic force is involved. So we have atoms existing because of the electromagnetic force. Now atoms come together to form chemical bonds with other atoms to create molecules. Now these bonds are also nothing but electromagnetic forces, the result of electromagnetic forces. So all kinds of molecules and the diversity of different molecular structures that you see are fundamentally a result of the electromagnetic force. So in a way, all chemical reactions and probably the entirety of chemistry is a result of electromagnetic forces, right? The crystal structures, the different kinds of crystals and solids which are possible is because of electromagnetic force. It also leads to the other properties which are associated with materials, the macroscopic properties which are a result of these chemical properties that arise due to the electromagnetic force. So for example, the optical properties of objects, why some objects are opaque, why some objects are transparent, why some objects radiate light in certain situations, as long as it's not radioactive. If it is dependent on some chemical reaction or chemical phenomena, it is a result of electromagnetic force. The electric and magnetic properties, why certain materials are insulators, some are conductors, is a result of electromagnetic force. And the internal structure of that particular material, or how the electron and the crystal structure are organized together. What about magnetic properties? Some materials behave as magnets, some do not. Some materials are susceptible to becoming magnets in the presence of an external magnet. It is also a result of electromagnetic force. The hardness, the softness, the elasticity of different materials is also a result of electromagnetic force. Whether some materials are solids, some are liquids, or some are gases at room temperature, that is also dependent on this particular forces. And the existence of light. Light is nothing but an electromagnetic oscillation. So all of these things, probably the vast variety of the world that we see around us, the chemicals, the chemical reactions without which life would not be possible, right? The vast variety of materials, solids, liquids, gases, they are all a result of this particular force. And this particular force fundamentally is a result of electric and magnetic fields. All right, so electric fields arise due to electric charges. So in the world we have electric charges, positive charges, negative charges, and they interact with each other. Like charges repel, unlike charges attract. You must have heard of the Coulomb's law, which gives us another inverse square law that tells us the force between these kind of charges. Now these charges interact via electric fields. All right, these charges are responsible for electricity. Okay, now when these charges start moving in a wire, let's suppose, then that leads to the creation of magnetic fields. All right, when you have bar magnets, the bar magnets have small magnetic dipoles, or basically the electron going around a particular atom. When many of these atoms align together, then the motion of the electron around an atom constitutes a current. And every current is associated with the magnetic field. So when all of these domains inside a particular material are aligned in a particular direction, you end up getting magnetic field lines. They give rise to the phenomena of magnetism. So electricity and magnetism are the result of the electromagnetic force. And electromagnetic oscillations. You know, when electric fields and magnetic fields affect one another, they lead to electromagnetic waves, which is light, is also a result of this particular force. How charges behave in the presence of electric and magnetic fields is given by the Lorentz force law. And in general, most of these phenomena are fundamentally explained in the same way gravitation was explained by Newton's law of gravitation. The electromagnetic behavior is explained by Maxwell's equations. Okay, so Maxwell's equations give us a kind of a complete understanding of electromagnetic behavior as far as classical physics is concerned. Okay, so it gives us an idea about how electric fields and magnetic fields arise due to one another, and what is the nature of electric fields and magnetic fields. All right, so Maxwell's equations give us a complete understanding as far as classical physics is concerned, and as far as explaining vast amount of macroscopic properties are concerned, the Maxwell's equations give us an understanding of the electromagnetic force. However, a modern explanation of electromagnetic behavior needs to incorporate quantum ideas. So the modern theory associated with electromagnetic force is known as the quantum electrodynamics, or QED. In short, what QED tells us is that when charged particles interact, then they interact via the transmission or mediation of light photons or virtual photons. So in general, this is part of the standard model of elementary particle physics. In standard model, different kinds of forces arise due to exchange of particles. Okay, so in gravitation, I did not talk about standard model. In gravitation also, quantum field theory tries to explain the mediation of gravity due to the exchange of some kind of a particle known as graviton. In the other forces also in standard model, especially in electromagnetism, the force is a result of exchange of photons. So what does this exchange mean? Well, in general, in the standard model of particle physics, the forces are said to exist as a result of exchange of particles. So if two objects are experiencing some kind of attractive or repulsive force, then there must be some kind of a particle which is exchanged between these two objects. And it is the exchange of this intermediary particle that leads to the attractive or repulsive force. So that is the general idea of how forces exist via exchange of particles or mediation of particles. So by absorbing a particle or recoil of a particle, you experience either attraction or repulsion. All right, so in that sense, quantum electrodynamics basically explains that, let's suppose two like charged particles like electrons experience some sort of a recoil or repulsion due to the exchange of a light photon or a virtual photon. I'll come back to this particular point a little bit later on. This in general is an idea incorporating the electromagnetic force. Let's move ahead to the next force, which is the strong nuclear force. All right, so I guess you guys are not bored yet, because we are coming to the most interesting part of the video, which is the strong force. All right, in here you are going to get a little bit of a flavor of the idea of particle physics and elementary particles in general. Okay, so the strong force, as the name suggests, is the strongest of all forces. Okay, even though it acts at extremely short distances of the order of the size of a nucleus, but at that distance it is the strongest out of all the fundamental forces, all the four fundamental forces. Okay, so in a way, you have a stable atom which has a positively charged nucleus and an electron. Now that atomic structure is a result of the electromagnetic force, right? But if you go inside the nucleus, you will find protons and neutrons as a collection. All right, now many protons exist together in a very small volume, in a region which is of the order of few femtometers. How is it possible? These protons repel one another, right? They have an electrostatic repulsion. They are positively charged. So how is it that so many protons exist together in a small collection called the nucleus? This is because another very powerful force exists in that distance, which is called the strong force. Now the strong force not only holds protons and neutrons together to create a nucleus, to create a stable nuclear structure, but it also holds quarks together to create the protons and the neutrons in the first place. So let me explain. Protons and neutrons are not fundamental particles. They are not elementary particles. If you break an atom, you get an electron, you get a nucleus. If you break a nucleus, you get protons, you get neutrons. But you can further break a proton or a neutron, or rather, you can see that they are a collection of further elementary particles which are known as quarks. Now I'm going to talk a lot about quarks and their properties maybe in some other video, but I'm going to give you a little bit of an idea just for this particular discussion. There are different kinds of quarks. You have up quark, down quark, top quark, bottom quark, charm, strange quark. These are called quark flavors, and 3 of these quarks end up creating what is known as a proton and a neutron. So a proton is made up of 2 up quark and 1 down quark. A neutron is made up of 1 up and 2 down quark. All right, the force that exists between these quarks, the force that holds these quarks together to create a proton and to create a neutron, is the strong force, which is also known as the strong nuclear force or the strong interaction or the color force. Why is it called color force? I'll come back to it in a moment. Now, this collection of quarks, which is a proton, and this collection of quarks, which is a neutron, are also attracted to each other, which is also a consequence of the strong force, but it is not known as a strong force. It is known as residual strong force or residual color force or just the nuclear force. This is because the force that exists between a collection of quarks, which is the nuclear force that holds the nucleus together, is a residual effect of a more fundamental strong interaction that exists between the quarks. Alright, so let me explain that a little more. So the strong force, therefore, I can classify into 2 sort of different categories. Okay, one is the strong force that exists between quarks, other is the residual force that exists between neutrons and protons, or also known as hadrons. Okay, hadrons is a class of particles of which neutrons and protons are a part of. So the strong interaction acts between quarks, alright, via gluons. I'll come back to it. Now, residual strong interaction acts between hadrons or neutrons and protons via exchange of pions or pi mesons. What are gluons? What are pions? Pions are kind of meson particles, which is also a kind of hadron particle, which consists of 2 quarks instead of 3. Gluons are fundamental massless boson particles that act as a mediator between the quarks. Now, what do I mean? Just now I explained in my previous discussion regarding electromagnetic force that in standard model, the existence of forces is explained by the exchange of some particle. If you have 2 objects attracting or repelling one another, then it is said that there must be an exchange of some particle happening. Alright, so if these 2 objects are continuously exchanging some other particle in between them, then the mediation of this particle leads to an attraction or a repulsion. This particle is known as a force carrier or a mediator. Okay, so all the fundamental forces in standard model are explained via the existence of some force carrier. Alright, in this case, the strong force is explained by the mediation of what is known as gluons. Okay, so gluons are the particles which are continuously being exchanged inside a proton between the quarks or inside a neutron. So inside the proton you have 2 up quark and 1 down quark which are continuously exchanging what are known as gluons in between them that leads to the effect of a strong force. Now this exchange of gluons that result in the strong force happens in distances of less than 0.8 femtometer, so within the dimension of a proton and a neutron. Now the interaction that happens inside the proton between these quarks is quite complicated. I will not go into the details of that. I'll just say that the exchange of the gluons lead to that strong force that holds the quarks to create a proton and a neutron in the first place. And the nature of the strong force is such that it is extremely powerful. It is so powerful that we have not yet been able to break apart a neutron and a proton to free up the quarks. Alright, we have not been able to free up the quarks. The quarks always remain inside a neutron or a proton or some other particle, because if you give energy to try to break apart a neutron or a proton, what happens is that instead of breaking the neutron or a proton apart into its individual quarks, the excess energy ends up creating a quark anti-quark configuration, which leads to creation of a new particle instead of breaking apart the older particle. This is known as quark confinement. Alright, so the strong force is extremely powerful, and In that sense, it has some other properties associated with it. It is not distance dependent. That means it is not dependent upon how far the quarks are. All right, they can be very far but still attracted to each other with the same amount of force. They depend on a quality known as color. Okay, you see I have drawn all these quarks with some colors. All right, green, red, blue. Now what is color? Well, in terms of strong force, which is explained by quantum chromodynamics, color is a property of quarks and gluons. All right, now this has nothing to do with the color that we see with our eyes. We see so many colors in our day-to-day life. This color has got nothing to do with that. It is just a name. All right, it has to do with the quantum property of these particles that somehow manifests itself, that we have named as a color because of certain reason, but it has nothing to do with the actual visual color. Now why we have named them as a color? Because it's a scene that the protons and neutrons are held together by quarks that have three different colors. So you see here red, green and blue. All right, now these three colors, we have a similar analogy in when you talk about primary colors. So it is a kind of an analogous to that. All right, so now in the electromagnetic force, we saw that charges, unlike charges attract, like charges repel. So what is charge? Charge is a property that can be positive or negative, right? And because based on that particular property, you end up getting electromagnetic force. In quantum chromodynamics, you have a property called color, and this color can be blue, green or red, and you can have a positive blue or a negative blue known as anti-blue. You can have a positive green and a negative green or anti-green. You can have a positive red and a negative red known as anti-red. So in the same way, in electromagnetic theory, you have charges, positive charges, negative charges. In quantum chromodynamics, you have colors, but three colors, okay? In electrodynamics, you have one charge, positive charge, negative charge, one property, but here you have three properties: blue anti-blue, green anti-green and red anti-red. And the way, and this is a property of the quarks and the gluons, and the way the properties manifest itself is that every time quarks come together to create different kinds of particles, they tend to create a collection of particles that do not have a color. So you see these hadrons here. These hadrons are colorless. You have a blue, green and red quark, so that ultimately this proton is colorless. You have a red, green and blue quark. Ultimately this hadron is colorless. This neutron is colorless. Other particles like mesons may have two quarks containing one color and one anti-color, so that it itself is also colorless. So in a way, these quarks come together to create stable particles which are colorless. All right, so these colors cancel each other out. So the color is a property in which these quarks and the gluons interact to create the strong force. Now I'm explaining color only for the sake of this discussion. I'll talk about it in more detail maybe in some other video later on in the series. So because of this reason that color is a property based on which quarks and gluons interact to create stable protons and stable neutrons, the theory associated with that is known as quantum chromodynamics. Okay, now usually the hadrons that we have are colorless. So colorless hadrons are not supposed to interact with one another, but this cancellation of the color is not 100%. There is a residual effect. So a collection of quarks may interact with another collection of quarks, a nearby quarks, and this force is a residual effect of the original strong force inside a proton or inside a neutron, and this is known as the nuclear force or the residual nuclear force. All right, and this residual nuclear force has slightly different properties. It acts between hadrons via the exchange of what are known as pi mesons or pions. So neutrons and protons, or protons and protons, or neutrons and neutrons are attracted to one another via the mediation of pi mesons, and they act in the distances of the order of 1 to 3 femtometers. This is very much a distance dependent force, because the further they are, the less significant the nuclear force becomes. This is why nucleus of infinite sizes don't exist. I mean, you have in the periodic table elements up to 100 or 120, right? Why? This is because for bigger nucleus, you need to have neutrons and protons which are very, very far away attracted to one another, but this does not happen. The nuclear force, which holds nucleus together by gluing the protons and neutrons together, only acts up to 1 to 3 femtometers. And when you have large nuclei, then those large nuclei experience electrostatic repulsion due to the protons. So a particular limit is reached beyond which the nuclear force is not able to hold the nucleus together, because the greater the size of the nucleus becomes, the more the electrostatic repulsion of the proton becomes. That is why you have a finite number of elements in the periodic table, finite number of stable nuclear configurations you have in the periodic table. All right, so coming back to the residual strong interaction, it exists between protons and neutrons via the exchange of pi mesons. And for the sake of the discussion, I want to show a very simple schematic of how this happens. So you have a proton and a neutron which interact with each other, or which experience force due to the mediation of a pi meson. This is a pi plus meson, which exchanged between both of them continuously to create the effect of a force. Okay, in this case you have 2 up and 1 down quark. They all have 3 different colors. In this case you have 1 up and 2 down quark. They all have 3 different colors. Now usually they are held together because of a continuous exchange of gluons in between them, but it may happen that sometime one of them may lead to the creation of a down quark and an anti-down quark having green color and anti-green color respectively. All right, now what this does is, this basically shuffles the configuration of this particular system. In this case you have up and down, but in this case now you end up getting up, down and down, and these two particles leave and end up creating a new particle, an up green quark and an anti-green anti-down quark. This is a positive pi meson which is emitted from this configuration, which is now a neutron, and it is rather later on absorbed by a nearby neutron which ends up becoming a proton. All right, so as you can see, a collection of quarks and another collection of quarks, which is a neutron and a proton in this particular case, may interact with one another via the exchange of a pi meson in between them, leading to the creation of the residual nuclear force. The nuclear force is responsible for nuclear fusion, different kinds of nuclear fission reactions. It is responsible for the elements that exist in our periodic table. It is responsible for the existence of hydrogen nucleus and all other nuclei, thus contributing to the very diversity of the different kinds of materials that we have. Because without a stable nucleus, you would not have a stable atomic configuration, right? So I'll talk more in detail about a nuclear force maybe in my further videos, but that's it for this particular force. Let's move ahead to the next force. Now the last force, the weak force. Now don't underestimate this force because its name is weak. It is in fact not that weak, okay? It is very much stronger than, let's suppose, gravitational force. So in the dimensions of within a neutron or a proton, this force is 10 to the power 25 times stronger than gravity. Okay, it's called weak force only because it's weaker than the strong force. All right, now this weak force is also very important inside a nucleus and inside neutrons and protons, because it leads to a very interesting interaction without which vast majority of the phenomena we see today would not be possible. So we have here the beta minus decay. So in the beta minus decay, what happens? I have an example here. A carbon 14 nucleus is converted to a nitrogen 14, in that process emitting an electron and an electron antineutrino, right? What's happening inside the carbon 14 nucleus? It's unstable because it has large number of neutrons. So one neutron gets converted to a proton, thereby emitting an electron and an electron antineutrino. Now I told you just some moments back that a neutron is 1 up and 2 down quark, and a proton is 2 up and 1 down quark. In this process, what is happening is when the neutron gets converted to a proton, basically a quark gets converted from one form to another form, or one flavor to another flavor. A down quark gets converted to up quark. Now in strong interaction or electromagnetic interaction, the change of a quark is not possible. The only interaction in which a quark can change from one to another, an up quark can change to a down quark, or a down quark can change to an up quark, is possible in weak interaction. All right, so if you see the Feynman diagram here, you have up, down, down quark in the neutron, which becomes an up, down, up quark in the proton, which is being mediated by what is known as a W minus vector boson. So weak interactions are mediated by W minus, W plus and Z vector bosons, which then decay into an electron and an electron antineutrino in this case. And in the beta positive decay, you have a positron and a neutrino. All right. So these kind of forces, they happen within the dimensions of a proton and a neutron. So in distances of the order of 10 to the minus 18 or 10 to the minus 17 meters. And the theory which describes their behavior is given by what is known as the electroweak theory. Okay, so I told you initially that electromagnetic interaction and weak interaction are separate. However, their explanations are given by a common theory which is known as the electroweak theory. All right, or the electroweak force, which can behave as electromagnetic force in certain situations and manifests itself as a weak force in other situations. So a kind of a unification of these two separate forces, and their explanation is given by the electroweak theory. And according to the electroweak theory, we end up seeing the different kinds of interactions which are possible in the weak interaction. All right, without the weak interaction, a very important thing is not going to happen in the world, and that is the nuclear fusion inside stars. So you know, inside the sun you have hydrogen nuclei which fuse to create deuterium nuclei. Deuterium nuclei fuse to create alpha particles. Alpha particles fuse to create higher elements, right? And this chain of nuclear fusion reactions leads to the release of energy. It leads to the creation of heavier elements. So all the elements in the periodic table that you see are created at the core of stars due to nuclear fusion reaction. Now this buildup of heavier elements would not be possible in the absence of a weak force. Why? Well, look at this reaction. You have two protons which fuse together to create a deuterium nuclei which contains a proton and a neutron. So you have two protons which created a proton and a neutron. That means in this process one proton got converted to a neutron. Now when a proton gets converted to a neutron or a neutron gets converted to a proton, it involves a change of a quark which is mediated by the weak force. So in this case, weak force is involved, which leads to the emission of positron and the neutrino in this particular case. Without the weak force, this kind of a fusion reaction is not going to be possible. So a buildup of heavier nuclei is not going to be possible. So you will not see the diversity of chemical elements in the periodic table that we see today. Without this weak force, you will not have certain kinds of nuclear fission reactions. You will not be able to see radioactive dating. All right. Now there is one more important point regarding weak force that I'll just briefly explain, that weak force is one of those forces which violates parity conservation. Strong force does not violate parity conservation. Electromagnetic force does not violate parity conservation. Only weak force does. What is parity conservation? Parity means reflection, a mirror reflection. All right. So if you look at the mirror reflection of a physical event, or you create the physical event by changing the physical apparatus to its mirror image, then both will give the same results. So it is basically a conservation of the left-handedness and the right-handedness of a physical event. Now in terms of strong interactions and electromagnetic interactions, the parity is conserved. That means a system does not prefer a left-handedness or a right-handedness. If you take the mirror image of an experimental setup, that will give you a result which will look like the mirror image of its original setup. All right, you get the point. So that is called parity conservation, which is not followed in the weak interaction. One more point regarding the weak force is that it basically gives us a kind of idea about the number of neutrons and protons in a given nucleus. So if you take a random element from the periodic table, you would find that the number of neutrons and protons in its nucleus is somewhat even. It follows the NZ graph. Okay, you will never find an element with a nucleus having mass number 100, out of which 99 are protons and 1 neutron. No, you won't find. Probably 60 out of those are neutrons and 40 out of those are protons. Okay, it basically follows the NZ graph. So what it means is that all the nuclei have somewhat even amount of protons and neutrons inside the nucleus. This is also a result of the weak force. So what happens is whenever number of neutrons exceeds the number of protons, the excess particle transforms into the other particle, thereby bringing their numbers equal. Or if the protons exceed the neutrons, the proton will get converted to a neutron. So it is because of weak force and the beta decay reactions as a result of the weak force, which brings about a kind of a near about even distribution of number of neutrons and protons in all the nuclei of the elements. All right, so these are the discussion of the different forces. Now let's do a final comparison of the strengths and some of the important points of all these four forces. Okay, the gravitational force, electromagnetic, strong, and the weak forces that we just now discussed. So here I have a table to compare the strengths of the different kinds of forces that we just now discussed. The gravitational force, electromagnetic force, strong force, and weak force. Okay, so the theory that describes these forces. So the gravitational force is described by the general theory of relativity. All right. The electromagnetic force is described by the quantum electrodynamics, QED. The strong force is described by quantum chromodynamics, and the weak force is described by electroweak theory. Now, if you take a look at the range of these forces, gravitation has an infinite range. There is no limitation to it. So does electromagnetic forces. It has an infinite range. One thing I forgot to mention while discussing electromagnetic forces is that even though electromagnetic forces has an infinite range, we don't necessarily see it manifesting itself in large scale planetary distances. This is because most of the time the different kinds of heavenly objects you see, planets, satellites, asteroids, they're electrically neutral. So electrically neutral objects don't really experience electromagnetic forces. Only when electrically charged objects are there, they will experience electromagnetic forces. The strong force has a range of around 10 to the minus 15 meters. So the distances of the order of nuclei. The weak force has even a smaller range, 10 to the minus 18 meters. Now, if you look at their relative strengths, we will start with the gravitation, which I have given here, the relative strength of 1. Okay. Now, of course, the relative strengths are different in different distances. So, of course, if I talk about distances of the order of few kilometers, then weak, nuclear, these forces are going to be insignificant in those distances, right? So, we are only doing a comparison for short distances. So, at extremely short distances, what is the relative strength between different forces? So gravitation, if it is 1, then electromagnetic force is 10 to the power 36 times powerful than gravitational force. Okay, that is huge amount. So if you take two protons few femtometers apart, they will repel with such force that the gravitational attraction is 10 to the minus 36 times smaller than the electromagnetic force. All right. The nuclear force is 10 to the power 38 times stronger than the gravitational force, and the weak force is 10 to the power 25 times stronger than the gravitational force. Now, if you talk about the force carrier, I did not mention the force carrier for gravitational force because I said the theory responsible for gravitation is GTR, which does not talk in terms of a force carrier. But in the standard model, all forces are explained by some kind of a force mediator. Okay, so quantum field theory tries to explain gravity in terms of a force carrier by proposing a hypothetical particle which is known as graviton. So it is important to note that a graviton has not yet been discovered, okay, but the hypothetical particle which quantum field theory tries to explain as the cause of a mediation between two massive bodies that results to gravitation is the graviton. All right, for electromagnetic force, the mediation of photon leads to electromagnetic attraction or repulsion. For strong force, between quarks, you have the exchange of gluons that leads to a strong interaction. Between neutrons and protons, or between hadrons, you have the exchange of pi mesons that leads to the attraction known as residual strong force. And for weak interaction, you have W plus, W minus, and Z vector bosons. So that is all for today's video. I hoped you understood the discussion, you learned something from it. I look forward to seeing you in the next coming videos. Thank you very much.